So, Zhiyu, this presentation will be presented by Zhiyu, the transform-based reasoning for learning evolutionary chain of events on temporal gauge. Let's have a try first. So, could you please make start?
Yeah. Hello, everyone. I'm very glad to be here to show our work about temporal knowledge graph. Today, the topic I'm going to talk about is transformer-based reasoning for learning evolutionary chain of events on temporal knowledge graph. Knowledge graph stores human summarized prior knowledge in structured data formats and are widely applied in many tasks, such as information retrieval, intelligent question answering, and recommendation system. Traditional knowledge graphs employ triples, each RET to record each fact or event in knowledge base, where EH and ET respectively represent the head and the tail entities, and R denotes the logical relation connecting these two entities. However, events in the real world often dynamically evolve over time. To extend the temporal nature of events, temporal knowledge graphs incorporate temporal information into the traditional triples, resulting in quadruples EH, R, ET, tau. For example, Barack Obama, President of USA from 2009 to 2017. However, existing temporal knowledge graph approaches still face two challenges. That is to say, they struggle to sufficiently explore the internal structure and semantic relationships within the virtual quadruples and to learn a unified representation of contextual and temporal correlation among different quadruples. To address the above problems, we propose a novel transformer-based temporal knowledge graph embedding called the transformer ECE former. And an end-to-end transformer-based network ECE former learns the evolutionary chain of events ECE for temporal knowledge graph reasoning. This work defines the subgraph composed of adjacent nodes that evolve over time along the query entity at the ECE. And an existing transformer-based module, the ECE former crafts specific module for handling intraquadruples and interquadruples respectively. For intraquadruples, ECE representation learning based on a transformer encoder is designed to explore the internal structure and semantic relationships within the virtual quadruples from the ECE. On the other hand, for interquadruples, mixed context knowledge reasoning involves a novel information mixing layer and an iterative transposition mechanism designed to explore the contextual and temporal correlations among different quadruples. The architecture of ECE former is shown in figure. Now I will introduce the details of our proposed method. First, let's introduce the evolutionary chain of events. We construct the query and its neighboring quadruples in the form of an ECE as shown in the red figure. Among them, C0 is the query quadruple and the rest are the neighbors of the query. For example, for the query George Bush VA2, question mask 2002 are shown in the red figure. ECE can formulate it as C equals George Bush VA2 2002. USA President of 21, Barack Obama succeeded 2009. Hence, our ECE can structurally represent both intraquadruples and interquadruples by encapsulating the dynamic evolution of entities and their interrelation within the event chain. The ECE can capture the historical and current events related to the subject entity. Now, I will introduce the learning representation for evolutionary chain events. The first key to effectively learning ECE lies in the comprehensive extraction and analysis of each triplet corresponding to the subnode of the ECE. Each component node of the ECE stores a historical event associated with the synchronicity, necessitating an investigation into its inherent structural and temporal characteristics. Inspired by the effective uniqueness of the transformer architecture in learning interdata dependencies, we introduced an SIGIR module utilizing a transformer encoder that distills the embedding of each triplet. Given a query queue, at P question method top and its ECE C sub Q, we treat each component within the branch of ECE as an individual token. For each triplet on the branch of the ECE, we append the special token data to CRS. Subsequently, we exploit the concatenation of semantic embeddings E and positional embedding P in the embedding space to represent each input token. These embeddings are interactively fed into the EC module. After encoding through the ECR, the embedded representation has effectively abstracted the relevant information of individual events. We introduce the query-specific contextual information to further enhance the accuracy of reasoning. Inspired by MLP Mixer, we introduced the MLP-based MCQR module to learn the multidimensional information interaction of the inputs by leveraging two mixing strategies. Different from the single event input in ECR, the MCQR module processes the sequence of Y plus K embeddings representations of ECE. This forms a two-dimensional real-valued input matrix A, M. The MCQR consists of M core units, each consisting of two key mixing layers, the channel MLP and the pattern MLP. The channel MLP operates on the columns of M aims to the facilitate information interaction across different events embedding within the same feature dimension. Conversely, the pattern MLP operates on the rows of M aimed to facilitate the information interaction within the same events embedding across different feature dimensions. Subsequently, we leverage a global average reporting layer to distill the mixed context, which can be formulated as equation 4. Given a quadruple with either the subject or the object missing, the task of link can be accomplished by computing the similarity between use of ECE and all candidate entities, which can be formulated as equation 5. In addition, to simulate the superior correlation between entities and the relationship promoted by conclusion information, we propose a max time prediction task to enhance the exploration of temporal information during the contextualization process. Specifically, we utilize a special token mask to replace the time-step tool in the query-specific branch of ECE to promote the model capability of understanding temporal information. We train the model using masked input to recover the perturbed time step. The methodology is likely to link prediction, where we directly utilize the unified representation use of ECE to predict the correct time step. For the link prediction and time prediction tasks, we employ the cross-entropy function to calculate the loss during the training process. The loss function can be formulated as equation 6. Now I will show the results of our ECE former experiments. We evaluate the performance of our proposed ECE former on 6 popular temporal knowledge graph benchmarks: PDRT, SEWS 05 to 15, SEWS 18, SEWS 14, Yago 11K, and Wikidata 12K. Considering that different methods are validated on various sets, we divide our experiments into two groups according to the dataset size for fair compensation. A noteworthy observation is that our ECE former significantly outperforms our other baseline models across all datasets in terms of MRR and HZK. Specifically, ECE former achieves performance improvements over the second best models by 14%, 6%, 5.7%, 5%, 0.4%, and 4.6% on MRR respectively, Additionally, it achieved gains of 9.7%, 12.6%, 11.2%, 8.5%, 1%, and 8.3% of T1, respectively. This significant margin of improvement demonstrates the superior performance of our EC former. To analyze the contribution of EC former components, we validated them and their variants on the ICWS14 and WikidS12K. From the results of ECR, we observed that by utilizing the transformer architecture, our module can surpass most geo information-based modules. Comparing the results of the ECR and EC former without TP, we observed that incorporating information significantly improves the module's reasoning accuracy on WikidS12K. However, this integration with in ICWS14 slightly diminished the performance. This is attributed to the general temporal granularity of ICWS14 compared to WikidS12K, where the frequent historical events in the context exacerbate superior correlations. Results in the vision of the task prediction task. The model is more prone to erroneous and oscillating. Comparing the results of EC former without TP and EC former, we observed consistent performance enhancements on both steps of executing the time prediction task. These findings confirm the effectiveness of our proposed temporal information enhancement strategy in prompting the model to leverage temporal information within its context, thereby effectively mitigating the impacts of superior correlation. In addition, we explore the performance fluctuation of EC former caused by the structural control parameters. N and M, where N represents the layer number in ECR and M represents the layer number in MCQR respectively. Our observation revealed that different structural settings to introduce perturbations to the module, with the disturbance being reactive manner at N2M equals 1 to 2, which is shown in the left table. Moreover, we also reported the results of the white coefficient lambda and the masking rate gamma. In the figure A, the performance curve turn suggests that if excessively weighting the time prediction task can detrimentally affect the link prediction task, thereby reducing overall performance. Therefore, setting the white weight coefficient between 0.5 and 1.0 offers a balanced improvement in model performance. In the figure B, we observe that as the masking rate increases, the model performance correspondingly improves. Notably, our final model is trained using a fully masked approach. In brief, in this paper, we address the challenge of completing missing factual elements in temporal knowledge graph reasoning by introducing the EC former, a novel end-to-end transformer-based reasoning model. EC former primarily comprises two key components: evolutionary chain of events representation learning (ECR) and the mixed context knowledge reasoning (MCQR). The ECR, utilizing the transformer encoder, thoroughly explores the structural and semantic information of historical events correspondingly to each branch in the evolutionary chain of events. The ECE is composed of neighborhood subgraph of NC nodes unfolded in chronological order. The MCQR, based on the MRP, relies on the channel and the pattern mixing strategy to facilitate the learning of contextual information interaction within the ECE. Moreover, additional time prediction task and time masking mechanisms are employed to force the model to simulate temporal information from the context. Comparative element experiments with state-of-the-art methods validate the superiority of our method. Furthermore, additional evaluation studies demonstrate the effectiveness of each module proposed in our EC format. That's all. Thank you for listening.